A valve is a mechanical device designed to regulate, direct, or control the flow of fluid by opening, closing, or partially obstructing a passageway. In pharmaceutical manufacturing, these components act as the primary interface between the product stream and the mechanical environment of the factory. Their engineering determines whether a system can maintain absolute sterility across reactors and utility networks, or if a leak allows external contaminants to enter the batch. A valve's unique internal geometry dictates its specific function, determining whether it provides full flow, fine throttling, or automated safety. Selecting an incompatible geometry for a specific fluid dynamic causes immediate issues, such as turbulent pressure buildup or structural fatigue. Because a single crevice or stagnant zone within a valve can harbor microbial growth, flow control must be subordinate to the requirements of hygienic design. Linear motion valves are defined by a closure rumber that moves in a straight line to stop or start the flow of fluid. The gate valve utilizes a flat vertical gate that moves up and down to block the passageway. This design allows for full, unobstructed flow with minimal pressure drop, which is why it is frequently used in water and clean fluid utility lines. The globe valve operates differently. A plug moves perpendicularly into the seat to control the fluid. While this plug allows for precise throttling, the obstructions in the flow path naturally lead to a loss of head pressure. The diaphragm valve uses a flexible disc that pushes down to form a seal against the body. This is the standard for sterile processing and handling corrosive fluids. Because it's isolated from the fluid, the valve is leak-proof and can be cleaned thoroughly without residue. Selecting a linear valve requires engineers to balance the need for unobstructed flow against the demands for precise regulation and sterile isolation. Rotary motion valves utilize a closure element that rotates 90 degrees, allowing for rapid operation of the line. A ball valve uses a spherical disc with a hole through the center to manage the flow of fluid. These valves provide tight sealing and require little maintenance, making them efficient for compressed air and solvent lines. Butterfly valves are built with a rotating central disc that matches the diameter of the pipe. Their lightweight and compact design makes them the preferred choice for HVAC and large-scale water systems where space is limited. The plug valve uses a tapered or cylindrical plug to handle gas lines and fluids that contain suspended solids. While linear valves offer precise tuning, rotary valves are selected for their speed and spatial efficiency across the facility. Some pipeline segments require passive protection and fine-scale adjustments rather than manual routing. A check valve allows fluid to move in only one direction and automatically closes if the pressure decreases. This prevents backflow, which protects pumps and upstream instrumentation from damage. Pressure relief valves provide safety by automatically venting excess pressure from boilers and reactors. For micro-adjustments, the needle valve uses a long tapered point on the end of the stem. The fine threads allow for the granular flow adjustments required in laboratory and instrumentation lines. These specialized valves either manage the most delicate flow adjustments or act as the final protection against catastrophic system failure. Pharmaceutical environments impose requirements on valves that go beyond simple mechanical function. Sanitary valves must be constructed from highly polished SS316L stainless steel to prevent bacterial adhesion and chemical corrosion. They are designed to withstand high-temperature clean-in-place and sterilize-in-place procedures without needing to be removed from the line. Specialized types include sampling valves for extracting product without introducing contamination, and drain valves installed at low points for complete fluid removal. Operators must ensure that internal seals and materials are compatible with the aggressive chemicals used during sterilization cycles. Maintaining these systems require following GMP validation protocols and performing regular calibrations to prevent leaks. A valve's ability to undergo repeated sterilization cycles without degrading its seals is as vital as its ability to control fluid flow. To see these principles in practice, consider the diaphragm valve as it is used in a purified water line. The specific internal architecture of this valve is what ensures the purity of the water remains uncompromised. A flexible diaphragm creates a physical seal that isolates the water from the moving mechanical parts of the actuator. This separation ensures that no mechanical lubricants or shed particles can migrate into the product stream. This geometry also eliminates dead legs, which are stagnant areas where bacteria could otherwise accumulate during the manufacturing process. Valves serve as the specific mechanical points that isolate the fluid stream and maintain the required hygienic conditions for manufacturing. Technical teams should utilize GMP compliance workshops and preventive maintenance diagnostic tools to ensure every valve in the facility performs to its specification. Correct valve selection ensures that the mechanical forces required for flow control do not compromise the safety of the final pharmaceutical product.